What we're going to do now is see how what you looked at in video 1, the tree diagram, ties together with what you saw in video 2, which was the multiplicative counting property. Our example here is that we have a jar containing 3 marbles, 2 black, 1 red. We're going to select a marble, put it back, draw a second marble, and we want to know the probability of getting 2 black marbles. In other words, the probability of BB. Let's start out with a tree diagram. Keep in mind, this is not a simple experiment. If we were just selecting 1 marble, that would be simple. And the fact that we're selecting 2 marbles, we have the first pick as well as the second pick, makes it complex. We have simple experiments strung together. So the tree diagram can help us organize our sample space and see all of our possible outcomes. Well, the first part of the tree diagram is the first stage of the experiment, namely the first pick. Well, we could get, you might be thinking, a black or a red marble. The second stage is the second pick. So here we assume we got a black marble on the first. We could get a black or a red marble on the second. Now, what if the red came out first? Well, keep in mind we're replacing. So we could get the red, or excuse me, we could get the black or the red to come out on the second pick. Even if the red came out on the first pick, because we're replacing it, it is an option for the second pick. If we read along the branches, we see our final outcomes. Black, 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 red, red, black, red, red. Based on this, you might be inclined to say that the probability of 2 black marbles is 1/4. Well, let's check this a different way. Let's use our counting property. Remember, the probability of any event is the ratio of success to total. So our job is to figure out the number of successes, the total number of outcomes, and express it as a ratio. Let's start with the number of success. Okay. Number of success. Success means getting a black marble and a black marble. So we have 2 picks. Let's start with the first. How many ways can a black marble come out on the first? 2. How many ways can a black marble come out on the second? 2. Since we need the first and the second pick together, that multiplicative property tells us we multiply, and that will tell us the total number of ways those 2 things can occur together, namely a black and a black marble. Now, as far as total possible outcomes go, the total possibilities for the first pick are 3. The total possibilities for the second pick, 3. Since we need the first and second pick together, that's what constitutes our final outcome. We multiply, and we see that we have 9 total outcomes. Expressing this as a ratio of success to total indicates that our probability of getting 2 black marbles is 4/9. That's quite different than our 1/4 probability found from the tree diagram. So why the discrepancy? Well, here's the thing. We didn't do anything wrong with our counting property, but we made a slight error with our tree diagram. The way the tree diagram is set up right now, it appears that the black and the red marble have an equally likely chance of coming out. The reality is they do not. There are more black marbles in this jar than there are white. So let's change up the tree diagram just a little bit. Let's treat each of those black marbles as the distinct outcome they are. That means that on the first pick, any one of those 3 marbles could come out. On the second pick, if black marble 1 came out, any one of the 3 marbles could come out with it on the second pick. If black marble 2 came out, again, any one of the 3 marbles could come out on the second pick. And keep in mind, since we have replacement, that means whatever we get first is going back in. Any one of the 3 marbles are fair game for the second pick. If we read along the branches, we see all the distinct outcomes. This is black marble 1 with black marble 1, black marble 1 with black marble 2, black marble 1 with the red. But maybe black marble 1 didn't come out at all on the first pick. Maybe it was black marble 2. Well, black marble 2 could have been paired with the other black marble, or black marble 2 came out both times, or maybe black marble 2 with the red. Finally, we can see everything that the red marble could be paired with had it come out first. If we look at this expanded tree diagram, we see that we have a total of 9 outcomes, and of those 9 outcomes, 4 of them qualify as success for getting 2 black marbles. This right here matches our work over here. The thing is about doing a tree diagram like this is that it can get terribly large and it can become very inefficient for finding sample spaces. Think about it. What if instead of just 2 black marbles and 1 red, what if I had 7 black marbles and 5 red? Now I would have to have 7 distinct outcomes for the black, 5 for the red. That's 12. So on my very first pick, I would have 12 possible outcomes. Branching off from those 12, I would have to branch off 12 more times for each of the 12 possible outcomes on the second pick. That's a very large tree diagram. And that's only considering 2 different colors. Okay, our experiments can be quite complex and have a lot of different possibilities. Thus, if we do it this way, we could end up with an extremely large tree diagram. There's a more efficient way of doing it, and it actually works off this tree diagram. So we're going to use this tree diagram, but we have to make sure that at some point we take into account that the black and red marbles do not occur with an equally likely chance. Let's take a look at what our revised tree diagram would look like. Our first pick could result in a black or red. Now you'll notice I was only treating them as distinct colors. I was not treating them, each of the black marbles, as a distinct outcome. I will take care of that by inserting probabilities. The black marble has a 2/3 chance of coming out on the first pick. There's 2 black marbles out of 3 in the jar. The red has a 1/3 chance. This now indicates that the black and red marble do not have an equally likely chance. On the second pick, a black or red marble could come out. Keep in mind they don't have an equally likely chance. The probability of black coming out on the second pick is still 2/3 and red is still 1/3. Now, what if the red came out first? Well, we could get a black marble on the first, or we could get a red marble on the second. Again, that red could come out because we are replacing. But again, we have to take into account the fact that they do not occur with an equally likely chance. So what do we do with these numbers? Well, first of all, let's just read across the branches and see these outcomes. We see those 4 different color combinations of 2 black, black-red, red-black, or red-red. What these color combinations do not take into account is all the different ways it could occur. So black-black could be from a black marble 1 with black marble 2, or black marble 2 with black marble 1. Could very well be that black marble 1 turned up twice, or black marble 2 turned up twice. So right here we have outcomes hidden inside. We don't know the distinct outcomes that generated this particular final outcome. Fact is, we're not really interested in all the different smaller combinations that make that black-black. We just want the all-encompassing black-black. So here's what we can do. If we take the probability of black turning up on the first pick and the probability of black turning up on the second pick, since we need both picks together, we can multiply. Now, multiplying fractions means multiplying across the top and multiplying across the bottom. There's that 4/9 probability we found from the counting property. Think about the counting property. When we figured out success, that was the number of ways black could occur on the first times the number of ways black could occur on the second. We multiplied 2 times 2, which is exactly what we did here. To figure out total possible outcomes, we took the number of possible outcomes on the first pick, which was 3, and we multiplied by the number of possible outcomes on the second pick, which was 3, and that gave us the total number of possible outcomes for both picks. Well, we multiplied 3 times 3 here as well. What we did previously was to find the number of success, find the total possible outcome, and then express it as a ratio. Over here, what we did was find the ratio of success to total first, and then multiply. You can do it in either order. It is faster to do it this way if you're working with a tree diagram. Okay, so what we see is the probabilities work just like the counting of the individual sets. This is known as the multiplicative property of probability. Now I could ask you another question. What's the probability of getting at least one black marble? Well, you have to really think about what at least one black marble means. What could those outcomes look like? That could be 2 black marbles, or that could be a black with a red, or that could be a red with a black. Remember, or is the key word for the union, and with the union we add. Now you could go back and look at that other tree diagram and count up the number of outcomes that qualify as success. And the expanded tree diagram would show you that 8 of those outcomes of the 9 qualify as having at least one black marble. The only outcome we can't count is that final one of red, red. But let's take a look at how we can get that answer from our condensed tree diagram. First of all, let's find the probabilities at the end of these branches. We see that the probability of black, black is 4/9. If I want the probability of getting black then red, what I can do is multiply the probabilities along this branch. In other words, take the probability of getting black on the first, which is 2/3, and multiply by the probability of getting red on the second, which is 1/3, and we see we have a 2/9 chance of getting this exact outcome. If we want to know the probability of red then black, we take the probability of getting red on the first, multiply by the probability of getting black on the second, and we get the final probability of 2/9, which is the probability of getting red then black. For red, red, we take the probability of red on the first times the probability of red on the second, and there's our 1/9 probability of getting the exact outcome of red, red. Now, we just finished saying that we could go back to that expanded tree diagram and count up our successes, which were 8, and count up our total, which was 9, and we have our probability of getting at least one black marble. But we said that those expanded tree diagrams are terribly inefficient. So how do we get our answer from this condensed tree diagram? Well, the probability of black, black occurs, or it has a 4/9 chance. The probability of black, red is 2/9. The probability of red, black is also 2/9. Or is the key word for the union, which is where we add. And when we add all these up, all these probabilities, we see our 8/9 probability. Why don't we need to worry about subtracting anything? Well, that's simple. That's because there is no overlap. If you get the outcome black, black, that means you did not get black, red, or red, black. If you get the outcome of black, red, that eliminates getting the other 2 outcomes. So they are distinct outcomes, very distinct outcomes. So we do not need to worry about subtracting anything. In the next video, we'll just look at the formal stating of the multiplicative property of probability, as well as what we just looked at here, which illustrates the additive property of probability.